Right now, as you watch this, you're surrounded by something that outweighs everything you can see by 6 to 1. It's not air, it's not dust, it's not any kind of normal matter at all. It's dark matter, and it's everywhere. In the space between your fingers, flowing through your body, filling every cubic centimeter of the cosmos with an invisible presence that holds galaxies together and determines the fate of the universe itself. These are the machine learning algorithms and neural networks, artificial intelligence systems that can see what human eyes cannot. The invisible 85% of all matter in our universe. This is breaking news from December 2025. And this is how convolutional neural networks and deep learning are finally mapping dark matter, the mysterious substance that shapes everything we know about reality. Imagine standing in a vast museum at night. The lights are off, and you can see almost nothing. But you have a flashlight with dying batteries that illuminates only 5% of the space around you. In that tiny circle of light, you see beautiful paintings, sculptures, artifacts of incredible craftsmanship. But 95% of the museum remains in absolute darkness. You know something is there. You can hear echoes, feel the space around you, sense the presence of massive objects, but you cannot see them directly. This is our universe. Everything we've ever observed, every star, every planet, every galaxy, every atom in your body, represents just 5% of all that exists. The rest is dark. Not dark because it's black, but dark because it doesn't interact with light at all. It doesn't emit light. It doesn't reflect light. It doesn't absorb light. It's fundamentally invisible to every telescope, every camera, every eye that has ever evolved. And yet, we know it's there. For nearly a century, this cosmic ghost has haunted physicists. They know it's there because they can see its effects, like watching footprints in snow from an invisible walker. Galaxies spin too fast. Clusters of stars move in ways that make no sense. The universe's largest structures exist in patterns that shouldn't be possible without something massive, something hidden, something dark pulling the strings behind the scenes. The implications are staggering. If most of the universe is made of something we cannot see, cannot touch, and barely understand, then everything we think we know about reality is incomplete. Our entire understanding of physics, built up over centuries of careful observation and experimentation, describes only a tiny sliver of cosmic reality. We're like microbes living on a grain of sand, trying to understand an ocean. But here's what's remarkable about this moment in history. We're no longer just hunting dark matter with telescopes and theories. We've enlisted artificial intelligence as our guide. And these digital detectives are revealing secrets about the invisible universe that have remained hidden since the beginning of time. The story begins in 1933 in the hills above Pasadena, California. The California Institute of Technology was home to one of the world's premier astronomical observatories. And working there was a Swiss astronomer named Fritz Zwicky. Brilliant, abrasive, and utterly unafraid to challenge conventional wisdom. And Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity, located about 320 million light-years from Earth. To understand what Zwicky discovered, you first need to understand what he was measuring and why it mattered. Galaxies aren't scattered randomly through space. They group together in clusters, held in gravitational embrace like dancers in a cosmic ballet. The Coma Cluster is one of the richest galaxy clusters we know, containing more than 1,000 galaxies, each containing billions of stars. The entire cluster spans roughly 20 million light-years across, a distance so vast that light itself, traveling at 186,000 miles per second, takes 20 million years to cross from one side to the other. Zwicky wanted to know how much mass this cluster contained. And it was a straightforward question with profound implications. By measuring how fast the galaxies were moving within the cluster, he could use Newton's laws of motion, laws that had successfully described planetary motion for centuries, to calculate the total mass holding them together. The principle is simple in concept. Imagine swinging a ball on a string in a circle above your head. The faster you swing it, the stronger the string must be to keep the ball from flying away. If you know the speed of the ball and the radius of the circle, you can calculate exactly how much force the string must provide. Gravity works the same way in galaxy clusters. The galaxies are like balls. Gravity is the string, and by measuring their speeds, you can calculate how much mass, how much gravitational string, is needed to hold them in place. And Zwicky carefully measured the velocities of galaxies in the Coma cluster by analyzing the light they emitted. When an object moves toward you, the wavelength of its light becomes slightly compressed, shifted toward the blue end of the spectrum. When it moves away, the light stretches out, shifting toward the red. This is the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you on the street. By measuring these red shifts and blue shifts, Zwicky determined that galaxies in the Coma cluster were moving at tremendous speeds, around 1,000 kilometers per second. For perspective, that's roughly 2.2 million miles per hour. These galaxies were moving so fast that, according to Newton's laws, they should have scattered into space long ago, like marbles rolling off a tilted table. But they hadn't scattered, and the cluster remained intact, held together by gravity. And this is where the mystery began. When Zwicky added up all the visible matter in the cluster, all the stars, all the gas, all the dust that telescopes could detect, he found that it wasn't nearly enough to generate the gravitational force needed to hold the cluster together. Not even close. The visible matter could account for only about 1% of the mass required. 99% of the mass was missing. Zwicky realized there had to be something else there. Something massive enough to hold these galaxies in their cosmic dance, but completely invisible to telescopes. He called it dunkle materie, dark matter. The name was descriptive, not poetic. This matter was dark simply because it couldn't be seen. For decades, though, his discovery was largely ignored. The idea seemed too strange, too unlikely. Surely there was a simpler explanation. Perhaps Zwicky had made an error in his calculations. Perhaps there was some unknown property of gravity that operated differently on cosmic scales. Perhaps there was luminous matter that telescopes had simply failed to detect. Faint stars, brown dwarfs, or clouds of gas too cool to emit visible light. But that simpler explanation never came. Instead, as observational techniques improved over the following decades, the evidence for dark matter only grew stronger. And it would take the work of another astronomer, working decades later, to finally force the scientific community to take dark matter seriously. In the 1970s, an astronomer named Vera Rubin was making observations that would fundamentally change our understanding of the cosmos. While working at the Carnegie Institution of Washington, Rubin studied not galaxy clusters, but individual galaxies themselves. She wanted to know how fast stars orbit within galaxies, a measurement that, like Zwicky's work, could reveal the distribution of mass. To understand what Rubin discovered, picture our solar system. The Sun sits at the center, containing 99.8% of all the mass in the solar system. The planets orbit this central mass, held in place by the Sun's gravity. Mercury, the closest planet, orbits at about 47 kilometers per second. Earth, farther out, moves at 30 kilometers per second. Neptune, at the solar system's edge, crawls along at just 5.4 kilometers per second. This pattern makes perfect sense according to Newton's law of gravitation. The strength of gravity decreases with distance. Objects farther from the center of mass move more slowly, following what's called a Keplerian decline, named after Johannes Kepler, who first described planetary motion in the 1600s. The relationship is precise and predictable. Velocity decreases proportionally to the square root of distance. Rubin expected to see the same pattern in galaxies. Most of a galaxy's visible mass, its stars, are concentrated in a bright central bulge. As you move outward from the center, the density of stars decreases. By the time you reach the outer edge of a galaxy's visible disk, there are very few stars. Logic suggested that stars at these outer edges, like Neptune in our solar system, should orbit much more slowly than stars near the center. But when Rubin made her measurements, she found something completely unexpected. She focused on spiral galaxies, galaxies like our own Milky Way, with arms of stars spiraling outward from a central bulge. Using spectroscopy, she measured the orbital velocities of stars at different distances from each galaxy's center. The technique was the same as Zwicky's. Measure the Doppler shift of light from stars, calculate their velocities. What she found contradicted everything that physics predicted. The stars at the edges of galaxies were moving just as fast as those near the center. Instead of slowing down with distance, as Keplerian dynamics demanded, the velocities remained roughly constant across the entire galaxy. This pattern, called a flat rotation curve, made no sense if galaxies contained only the matter we could see. Let me be clear about how strange this is. Imagine if Neptune orbited the Sun at the same speed as Mercury, 30 times faster than it actually does. That would violate everything we know about how gravity works. It would mean there was some massive, invisible source of gravity beyond Neptune's orbit, tugging on it, speeding it up. That's exactly what Rubin's flat rotation curves implied. There had to be enormous amounts of invisible mass extending far beyond the visible edges of galaxies. A vast halo of dark matter, perhaps 10 times more massive than all the visible stars, gas, and dust combined. Rubin observed galaxy after galaxy, and in every case, she found the same pattern. Flat rotation curves, invisible mass, dark matter. This time, the scientific community couldn't ignore it. Rubin's observations were too precise, too consistent, too reproducible. Combined with Zwicky's earlier work on galaxy clusters, and with additional evidence from gravitational lensing and the cosmic microwave background radiation, the case for dark matter became overwhelming. But perhaps the most dramatic evidence came from the Bullet Cluster, a cosmic collision where two galaxy clusters smashed into each other at tremendous speed. When astronomers mapped both the visible matter through X-ray emissions and the gravitational mass through weak lensing, they found something remarkable. The dark matter had separated from the normal matter during the collision. The hot gas slammed together and slowed down, but the dark matter passed right through, unimpeded. It was the first direct observational proof that dark matter and normal matter are distinct substances. But Rubin's path to this discovery had not been easy. She faced obstacles that had nothing to do with science. When she applied to observe at Palomar Observatory in 1965, home to the 200-inch Hale telescope, then the most powerful telescope in the world, she was told her observing time would be limited because the facility didn't have a women's restroom. It was a common excuse to exclude women from major astronomical institutions. Undeterred, Rubin made her own restroom by sticking a paper sign on a door. Despite such barriers, Rubin persisted. Her work fundamentally changed our understanding of the cosmos. Yet, she was never awarded the Nobel Prize, an omission many consider one of the most glaring oversights in the history of the award. Rubin died in 2016, still unrecognized by the Nobel Committee, though she received nearly every other major prize in astronomy. And as she once said, "There's no problem in science that can be solved by a man that cannot be solved by a woman." Her legacy stands as proof of that statement. Today, we know that dark matter makes up about 27% of everything that exists. Combined with dark energy, a mysterious force causing the universe's expansion to accelerate, which makes up another 68%. The dark components of reality account for 95% of the universe. Everything we can see, stars, planets, galaxies, and life itself, represents just 5% of cosmic reality. We're living in what's essentially a sliver of existence, a thin layer of the visible floating on an ocean of the invisible. But what exactly is dark matter? What is this substance that outweighs normal matter by more than 5 to 1, yet remains completely invisible? First, let's clarify what dark matter is not. It's not dark in the sense of being black. Black objects absorb light. Dark matter doesn't interact with light at all. It doesn't emit it, absorb it, or reflect it. You could shine the brightest flashlight in the universe directly at a clump of dark matter, and the light would pass right through as if nothing were there. Dark matter is also not antimatter. Antimatter is well understood in physics. It's regular matter with opposite electrical charge. When matter and antimatter meet, they annihilate in a burst of gamma rays. If dark matter were antimatter, we'd see these gamma ray signatures all over the universe. We don't. It's not black holes. While black holes are indeed dark, they create powerful gravitational effects that would be easily detectable. We can spot black holes by observing how they pull on nearby stars and how they distort light. If dark matter were made of black holes, we'd see these effects. We don't. It's not normal matter that's simply too faint to see. Old dead stars, brown dwarfs, or cold gas. Surveys have been conducted to search for such objects, and while they do exist, they're far too rare to account for dark matter. Moreover, the abundance of light elements created in the Big Bang, hydrogen, helium, and lithium, tells us exactly how much normal matter can exist in the universe. Dark matter far exceeds this limit. So what is it? The leading hypothesis is that dark matter consists of new, undiscovered particles, matter of a type never before encountered in nature. These particles would be fundamentally different from the protons, neutrons, and electrons that make up everything familiar to us. They would interact through gravity, which is why we can detect their gravitational effects. But they would barely interact through any other force. The most popular candidate is called a WIMP, a weakly interacting massive particle. True to its name, a WIMP would be massive enough to have significant gravitational influence, but would interact with normal matter only through the weak nuclear force and gravity. The weak force is so feeble that WIMPs could pass through the entire Earth without hitting a single atom. Trillions of them may be passing through your body right now, like ghosts through walls, completely unnoticed. Other candidates include axions, extremely light particles proposed to solve certain problems in quantum physics, and sterile neutrinos, hypothetical cousins of the known neutrinos that interact even more weakly with matter. The truth is, we don't know what dark matter is made of. But we know it exists. We know how much of it there is, and we know how it's distributed throughout the universe. And that knowledge comes from observing its gravitational effects with ever-increasing precision. Understanding how we detect dark matter requires understanding gravity itself, not as a force pulling objects together, but as a curvature of space and time. In 1915, Albert Einstein revolutionized physics with his general theory of relativity. Newton's description of gravity as a force between masses worked brilliantly for most purposes. But Einstein showed that gravity is actually something far stranger. Mass doesn't pull on other mass directly. Instead, mass warps the fabric of space-time itself, creating curves and valleys. Other objects then move along these curves, like marbles rolling along the contours of a rubber sheet, stretched and distorted by a bowling ball. This geometric picture of gravity leads to a remarkable prediction. Light, despite having no mass, should be affected by gravity. Light should follow the curves in space-time created by massive objects. And since dark matter has mass, lots of it, it should bend light. This phenomenon is called gravitational lensing, and it's one of the most powerful tools we have for mapping dark matter. Imagine you're looking at a distant galaxy billions of light years away. Between you and that galaxy, there's a massive cluster of galaxies, a collection like the Coma cluster that Zwicky studied. The cluster's enormous mass warps space-time, creating a gravitational lens. Light from the distant background galaxy travels through this warped space, and its path bends, just like light bending through a glass lens. From Earth, we see the background galaxy in a distorted form. It might appear stretched into an arc, or smeared into multiple images, or magnified and brightened. The specific pattern of distortion depends on the distribution of mass in the foreground cluster, including, crucially, the distribution of dark matter. By carefully analyzing these distortions, measuring exactly how much light has been bent, from exactly which directions, astronomers can create maps of where mass is located in the intervening space. And when they do this, they find something remarkable. The mass concentrations don't match the locations of visible galaxies. The mass extends far beyond visible matter, creating dark matter halos that dwarf the galaxies they surround. This technique, called weak gravitational lensing when the distortions are subtle, has become one of our primary methods for mapping dark matter across the universe. And it generates data of staggering complexity. A typical gravitational lensing survey might analyze images of hundreds of millions of galaxies. Each galaxy's shape must be precisely measured. The distortions must be separated from the galaxy's intrinsic shape. You're trying to figure out how much a galaxy has been stretched by lensing versus how stretched it naturally is. You must account for atmospheric distortion, telescope optics, cosmic rays hitting the camera, and 1,000 other confounding factors. The data is noisy, subtle, and high-dimensional. For decades, astronomers used statistical techniques to extract dark matter maps from this data. Techniques that worked, but were limited by the human ability to conceive of and test different models. And then, artificial intelligence entered the picture, and everything changed. To understand why artificial intelligence has become essential to dark matter research, you need to appreciate the sheer scale of data modern astronomy generates. Consider the Sloan Digital Sky Survey, which began operations in 2000. This survey was revolutionary for its time. Using a dedicated 2.5-meter telescope in New Mexico, it systematically photographed the night sky, creating the most detailed three-dimensional map of the universe ever made. By the time these observations concluded in 2008, they had imaged more than 1/4 of the entire sky and cataloged hundreds of millions of celestial objects. The data set was massive. Over 15 terabytes of information, including photometric measurements, spectroscopic data, and millions of images. Analyzing this data using traditional methods took years and required armies of graduate students and postdoctoral researchers manually inspecting spectra, classifying galaxies, and running statistical analyses on subsets of the data. But that was just the beginning. The Dark Energy Survey, which ran from 2013 to 2019, imaged 5,000 square degrees of the southern sky with a 570 megapixel camera, one of the most powerful astronomical cameras ever built. It observed 300 million galaxies and 100 million stars, and the data set exceeded 3 petabytes, 3,000 terabytes of raw information. Processing this required not just human effort, but sophisticated automated pipelines. Computers automatically calibrated images, identified objects, measured their properties, and flagged anomalies for human review. Even so, fully exploiting the scientific value of this data has taken years and engaged hundreds of researchers worldwide. And now, we're entering a new era entirely. The Vera C. Rubin Observatory, named in honor of the astronomer who discovered dark matter's gravitational signature, is currently under construction in Chile. When it begins operations, Rubin Observatory will revolutionize astronomy. Its 3.2 gigapixel camera will photograph the entire southern sky every few nights, creating a movie of the universe that captures anything that changes or moves. Over 10 years, Rubin Observatory will generate approximately 60 petabytes of data. That's 60,000 terabytes. Roughly equivalent to the entire text of every book ever written, multiplied by 100,000. Every night, Rubin Observatory will produce about 20 terabytes of raw data. It will discover an estimated 10 million transient events, supernovae, asteroids, variable stars, every night. Human astronomers cannot possibly review all of these. Even if you had 1,000 astronomers working full-time, they couldn't keep pace. This is where artificial intelligence becomes not just helpful, but absolutely necessary. The fundamental challenge in analyzing astronomical data, especially for dark matter research, is pattern recognition at enormous scale. When you look at a gravitational lensing image, you're trying to identify subtle distortions in galaxy shapes caused by intervening dark matter. But these distortions are tiny, often just a few % elongation of a galaxy's natural shape. And galaxies come in an enormous variety of intrinsic shapes. Some are circular, some are elliptical, some are spiral, some are irregular. How do you separate the intrinsic shape from the lensing distortion? Traditionally, astronomers built physical models of galaxy shapes based on theoretical understanding and observations. They'd assume galaxies follow certain mathematical distributions of shapes, then use statistical techniques to infer the lensing signal. This worked, but it required making strong assumptions about what galaxies should look like. It also struggled with complexity. Real galaxies are messy. They have asymmetries. They merge with other galaxies, creating tidal tails and streams. They have dust lanes that obscure parts of their light. Each of these features can mimic or mask lensing signals. Human experts can sometimes identify these features by eye, drawing on intuition developed over years of experience. But human analysis is slow, subjective, and doesn't scale to billions of galaxies. Computers, on the other hand, excel at exactly this kind of task, if they're properly trained. Machine learning, at its core, is about finding patterns in data without being explicitly programmed with rules. Traditional computer programming works by giving a computer explicit instructions. If you see X, do Y. This works well for tasks where the rules are clear and can be articulated. But for complex tasks like identifying galaxy shapes or detecting subtle gravitational lensing signatures, the rules are too complicated to write down explicitly. Machine learning flips this around. Instead of giving the computer rules, you give it examples. You show it thousands or millions of examples of what you're looking for, along with labels indicating what each example represents. The computer then discovers patterns that distinguish one type of example from another. For astronomical applications, this typically involves neural networks. computational systems loosely inspired by how neurons in the brain connect and process information. Imagine you want to train a neural network to recognize gravitational lensing arcs. You'd start by showing it thousands of images, some containing real lensing arcs, and some containing other features that might be confused with arcs: galaxy arms, foreground objects, image artifacts. Each image is labeled lensing arc or not lensing arc. The neural network is essentially a massive mathematical function with millions of adjustable parameters called weights. Initially, these weights are set randomly, and the network's outputs are nonsense. But the network can adjust its weights based on feedback. When shown a training image, the network makes a guess. Is this an arc or not? If it guesses correctly, the weights are slightly adjusted to reinforce that correct behavior. If it guesses wrong, the weights are adjusted to make that mistake less likely in the future. This happens millions of times, across thousands or millions of training examples. Gradually, through this iterative process, the network learns to recognize patterns that distinguish lensing arcs from other features. Crucially, it learns these patterns from the data itself, without anyone having to explicitly program rules like an arc should be this curved or should have this brightness profile. The result is a system that can often match or exceed human expert performance, while processing images at speeds no human could match. For image analysis, which is central to dark matter research, a specific type of neural network called a convolutional neural network has proven extraordinarily powerful. These networks are designed to process grid-structured data like images. They work by applying a series of filters, mathematical operations that scan across an image looking for specific features. Your early layers in the network might learn to detect simple features: edges, corners, color gradients. Deeper layers combine these simple features to detect more complex patterns: curves, symmetric structures, specific arrangements of shapes. For gravitational lensing analysis, a network might learn in its early layers to detect edges and brightness gradients in galaxy images. Middle layers might learn to recognize elliptical shapes and their orientations. Deep layers might learn to identify the specific patterns of distortion characteristic of gravitational lensing, subtle correlations in how nearby galaxies are aligned, or the characteristic tangential stretching around a mass concentration. The remarkable thing is that the network learns all of this automatically, simply by being shown many examples and being rewarded for correct classifications. No astronomer had to manually program these feature detectors. The network discovered them through training. This capability extends far beyond just classifying individual images. Modern deep learning systems can segment images, identifying which pixels belong to which objects. They can measure properties like position, brightness, shape, and color with high precision. They can denoise images, removing artifacts while preserving real astronomical features. They can in-paint missing data, filling gaps in observations. They can super-resolve images, enhancing detail beyond the telescope's native resolution. They can detect anomalies, flagging unusual objects for human review. They can generate realistic simulated data for testing analysis pipelines. Each of these capabilities is directly useful for dark matter research. There's another critical way AI helps with dark matter research: by learning from simulations. Since we can't directly experiment with dark matter in a laboratory, cosmologists rely heavily on computer simulations. They write equations describing how dark matter should behave based on physics. Run these equations forward in time, starting from the Big Bang, and see what structures emerge. These simulations are computationally intensive. A state-of-the-art dark matter simulation might track the motion of billions of particles over cosmic time, requiring months of processing on supercomputers. The output is a detailed, three-dimensional map of how dark matter should be distributed in a simulated universe. By running many such simulations with different parameters, different amounts of dark matter, different properties of dark energy, different starting conditions, cosmologists can explore how the universe would look under various scenarios. The challenge is connecting these simulations to real observations. A simulation gives you the true dark matter distribution. Real observations give you distorted galaxy shapes, noisy measurements, and incomplete data. How do you infer the former from the latter? This is where AI excels. You can train a neural network using simulated data where you know the ground truth. Show the network simulated lensing images, along with the actual dark matter distributions that created them. Let it learn the complex, nonlinear relationship between observed distortions and underlying mass. Once trained, you can apply the network to real observations. The network has learned how to see dark matter through the patterns it creates in galaxy distributions, patterns too subtle and high-dimensional for human analysis. This simulation-based training approach has become central to modern cosmological AI. It allows researchers to leverage the full complexity of their theoretical understanding, encoded in simulations, to extract maximum information from observations. In 2019, researchers at ETH Zurich made a breakthrough that changed the field of dark matter research forever. Dr. Janice Fleury, then a PhD student, led a team that trained machine learning algorithms to analyze images of galaxy clusters. Their goal was ambitious: teach computers to recognize the subtle distortions that dark matter creates in space-time itself, and use those distortions to map dark matter with unprecedented precision. The team started with simulations, artificial universes generated by supercomputers running the equations of cosmology forward from the Big Bang. These simulations included both dark matter and normal matter, evolving over billions of years to create galaxies, galaxy clusters, and cosmic structure. From these simulations, they generated synthetic observations, what a telescope would see when looking at these simulated structures. This included the gravitational lensing effects, background galaxies distorted by dark matter in foreground clusters. They then trained a convolutional neural network to analyze these synthetic observations and infer the dark matter distribution. Then the network learned to recognize patterns that no human astronomer had explicitly identified. Correlations across multiple galaxies, subtle statistical signatures in shape alignments, complex relationships between foreground cluster galaxies and background source distortions. When they tested the trained network on real observations of actual galaxy clusters, the results were stunning. The AI could identify dark matter's gravitational fingerprints with precision that exceeded traditional analysis methods by a significant margin. It was, as Fleury described it, teaching computers to see the invisible. This is the first time such machine learning tools have been used in this context, Fleury explained. The implications were clear. AI had just opened a new window on the dark universe. But this was just the beginning, when what Fleury's team had demonstrated was a proof of concept. The real revolution would come as these techniques were scaled up, refined, and applied to much larger datasets. Following the ETH Zurich breakthrough, AI applications in dark matter research exploded. At University College London, Dr. Niall Jeffrey and his team took the simulation-based approach to new levels. They used AI to analyze entire mock universes, not just individual clusters, but cosmic-scale simulations spanning billions of light years and billions of years of evolution. Their neural networks learn to recognize how dark matter and dark energy shape cosmic evolution at the largest scales. The networks analyze the distribution of galaxies across space and time, the growth of cosmic structure, the statistical properties of the cosmic web, the universe's large-scale structure, where galaxies cluster along filaments of dark matter separated by vast voids. The results exceeded all expectations. Using AI to learn from computer-simulated universes, we increased the precision of our estimates of key properties of the universe by a factor of 2, Jeffrey reported. A factor of 2 improvement in precision is, in astronomy, extraordinary. To put this in perspective, imagine you're trying to measure the mass of dark matter in a galaxy cluster. With traditional methods, you might determine the mass to within plus or minus 20%. With AI-enhanced analysis, you could narrow that uncertainty to plus or minus 10%. That doubling of precision is equivalent to having twice as much data. In fact, Jeffrey's team calculated that their AI improvement was equivalent to suddenly having data from 300 million additional galaxies. Data that would take years to collect with current telescopes. The AI wasn't just processing data faster, it was extracting more information from the data that already existed. This is a crucial point worth emphasizing. AI doesn't just speed up analysis, it finds patterns and correlations that traditional methods miss entirely. It's not doing the same analysis faster, it's doing better analysis. What makes these AI systems so powerful for dark matter research? The answer lies in how they're constructed and what they've learned to recognize. Modern astronomical AI typically uses deep convolutional neural networks with specialized architectures tailored to the physics of the problem. For gravitational lensing analysis, networks often use an encoder-decoder structure. The encoder progressively compresses an image into a low-dimensional representation, a compact mathematical description capturing the image's essential features. The decoder then expands this representation back out into a dark matter map. During training, the network learns to make this representation encode exactly the information needed to reconstruct the dark matter distribution. Irrelevant features, noise, individual galaxy appearances, foreground contamination, are learned to be discarded. Relevant features, correlated distortions, coherent alignments, statistical patterns, are learned to be preserved and amplified. Some networks use attention mechanisms, components that let the network learn to focus on certain regions or features while ignoring others. For example, the network might learn to pay more attention to regions with many background galaxies, where the lensing signal is stronger, and less to regions with few sources. Others use residual connections, architectural features that help train very deep networks by allowing information to flow directly from early to late layers. This helps the network learn both fine details and large-scale patterns simultaneously. Still others incorporate physical priors, knowledge of physics built directly into the network architecture. For example, gravitational lensing obeys certain symmetries and conservation laws. By building these symmetries into the network structure, researchers can improve performance and reduce the amount of training data needed. The key insight is that these networks aren't black boxes operating on pure statistics. They're carefully engineered systems that combine deep learning's pattern recognition power with domain knowledge from physics and astronomy. One criticism of deep learning is that it's a black box. You get accurate predictions, but you don't know why the network made those predictions. For scientific applications, this opacity is problematic. Scientists want to understand not just what the AI found, but how it reached its conclusions. This has led to growing interest in interpretable AI, systems that can explain their reasoning. Researchers have developed something called interpretable AI systems for dark matter research. Unlike traditional neural networks, these systems can show scientists exactly how they reach their conclusions about dark matter. They break down their analysis into components that correspond to physically meaningful features. I identified a mass concentration here, based on this pattern of tangential shearing in these background galaxies. Or, I detected a dark matter filament connecting these two clusters based on this statistical correlation in galaxy orientations. This interpretability is crucial because it allows scientists to understand not just what the AI is finding, but why. They can verify that the network is picking up on real physical signals rather than spurious patterns in the data. They can gain intuition about what features in the data are most informative. And they can use the network's learned features to develop new, purely analytical methods. In essence, interpretable AI turns the machine learning system into a research partner rather than just a tool. It becomes a source of insight, suggesting new ways to think about the data that human scientists can then build upon. On July 1st, 2023, a European Space Agency rocket lifted off from Cape Canaveral, carrying the Euclid Space Telescope into orbit. Euclid is unlike any previous space telescope. While Hubble was designed for deep, detailed observations of small patches of sky, and the James Webb Space Telescope focuses on the most distant galaxies in infrared light, Euclid has a different mission: to map the dark universe across a third of the entire sky. Over 6 years, Euclid will observe 1.5 billion galaxies. Yes, billion with a B, spanning 15,000 square degrees of sky. It carries a 600 megapixel camera, one of the largest digital cameras ever sent to space. This camera observes invisible light and near-infrared, capturing images with extraordinary clarity, unimpaired by Earth's atmosphere. The data Euclid is generating is staggering in scope. In just the first week of science operations, the telescope captured images of 26 million galaxies. Some of these galaxies are so distant that their light has been traveling toward us for 10.5 billion years. We're literally seeing the universe as it was when it was just a quarter of its current age. Processing this cosmic flood of information would be absolutely impossible without AI. Dr. Mike Walmsley from the University of Toronto, an expert in astronomical deep learning and creator of the Zubot system, puts it perfectly. We're at a pivotal moment in terms of how we tackle large-scale surveys in astronomy. AI is a fundamental and necessary part of our process in order to fully exploit Euclid's vast dataset. This isn't hyperbole. Let me quantify the challenge. Over its 6-year mission, Euclid will generate approximately 850,000 images. Each image contains thousands of galaxies. Each galaxy must be identified, its position measured, its shape characterized, its redshift estimated, its properties cataloged. Gravitational lensing signatures must be extracted from the correlated shapes of hundreds of galaxies per square arc-minute of sky. If you assigned this task to human astronomers and gave each galaxy just 30 seconds of analysis time, barely enough to look at it, it would take a single person working full-time, with no breaks, be over 1,400 years to process Euclid's complete dataset. AI processes this in days or weeks, not centuries. Euclid's AI analysis pipeline includes a fascinating example of human-AI collaboration, a system called Zubot. Zubot is a neural network trained through citizen science. The Galaxy Zoo project, launched in 2007, invited members of the public to help classify galaxies from telescope images. Over 1 million volunteers have participated, providing over 70 million individual classifications. These human classifications became training data for machine learning. Researchers trained Zubot on images where thousands of humans had already identified features like spiral arms, central bulges, bars, mergers, and irregular structures. The network learned what features humans consider salient and how to classify galaxies according to human perception. For Euclid, this human-AI partnership has already categorized more than 380,000 galaxies from initial data releases. The network can classify galaxies according to detailed morphological features, structure, symmetry, arms, bars, disturbances, with accuracy matching human expert consensus. What's remarkable is that the network isn't just mimicking human classifications. It's learned general principles of what makes one galaxy different from another. It can classify galaxies in ways humans never explicitly taught it, by combining features humans identified into novel categories. Researchers playfully call this Facebook for galaxies. Just as Facebook's algorithms learn to recognize eyes, mouths, and ears in photos to identify faces, Zubot learns to recognize arms, bulges, and bars to identify galaxy types. And just as Facebook's system can work on photos it's never seen before, Zubot can classify new galaxies from Euclid's unprecedented image quality. As Tomasz Kasperzak from ETH Zurich explained, Facebook uses its algorithms to find eyes, mouths, or ears in images. We use ours to look for the telltale signs of dark matter and dark energy. Euclid's AI systems don't just process images after they're downloaded to Earth. Some analysis happens in near real time, identifying interesting targets for follow-up observation while they're still fresh. When Euclid images a patch of sky, these automated algorithms immediately search for strong gravitational lensing events, rare cases where a massive foreground object creates multiple images or dramatic arcs of a background source. They hunt for supernovae, exploding stars that can be used to measure cosmic distances and test dark energy models. They identify unusual galaxies, objects that don't fit standard categories and might represent new physics. They flag transient events, anything that's appeared or changed since previous observations. The system flags these discoveries for human review within hours. Astronomers can then trigger observations with other telescopes while the event is still evolving, crucial for time-sensitive phenomena like supernovae. This rapid turnaround is only possible because A, I can screen millions of galaxies and identify the rare, the interesting needles in the cosmic haystack without human intervention. One of Euclid's primary science goals is mapping the cosmic web, the large-scale structure of dark matter throughout the universe. If you could see dark matter, the universe would look like a vast, three-dimensional web. Dense filaments of dark matter stretch across hundreds of millions of light-years, connecting galaxy clusters like beads on a string. Between these filaments lie enormous voids, regions nearly empty of both dark matter and galaxies. This structure arose from quantum fluctuations in the infant universe, tiny ripples in density that grew over billions of years through gravitational attraction. Dark matter clumped together first, and normal matter followed, falling into the dark matter's gravitational wells. Galaxies formed where dark matter concentrations were densest. Understanding this cosmic web's detailed structure tests our models of cosmology, dark matter, and dark energy. Different models predict different web geometries, thicker or thinner filaments, larger or smaller voids, different degrees of clustering. Euclid's observations, combined with AI analysis, are revealing this structure with unprecedented clarity. By measuring how strongly gravity has lensed background galaxies across different regions of sky. AI systems reconstruct three-dimensional maps of dark matter distribution. These maps show not just where dark matter is, but how it's organized. They reveal how dark matter halos surround galaxies, how filaments connect these halos, how structure has evolved over cosmic time by comparing nearby and distant regions, where voids and supervoids exist, and how dark energy has affected structure growth. Early results from Euclid have already revealed dark matter structures never seen before. Bridges of dark matter connecting galaxy clusters across 50 million light-years. Dark matter caustics where filaments intersect, and massive voids seemingly devoid of both matter and dark matter. Each of these discoveries tests our theoretical models. Do simulations predict these exact structures? If not, what physics might we be missing? While astronomers map dark matter's gravitational effects across the cosmos, particle physicists are hunting dark matter on Earth through direct detection experiments. The logic is elegant. If dark matter pervades the universe, it must be flowing through Earth right now. As our planet orbits the Sun, and the Sun orbits through the galaxy, we're moving through a sea of dark matter particles. If these particles occasionally interact with normal matter, even incredibly rarely, we should be able to catch them. The challenge is incredibly rarely. Dark matter is weakly interacting almost by definition. A WIMP might pass through the entire Earth without hitting a single atom. Your body is transparent to dark matter. Trillions of WIMPs may pass through you every second without leaving any trace. To catch even one dark matter particle requires extraordinary sensitivity and extraordinary patience. Enter the Lux-Zeppelin experiment, known as LZ. Deep beneath the Black Hills of South Dakota, nearly a mile underground in a former gold mine, sits one of the most sophisticated scientific instruments ever built. The Lux-Zeppelin detector occupies a cavern that once hosted another groundbreaking neutrino experiment, led by Nobel laureate Raymond Davis Jr. The location isn't arbitrary. Being underground provides shielding from cosmic rays, high-energy particles from space that constantly bombard Earth's surface. Cosmic rays would create background noise that could mimic dark matter signals. A mile of rock overhead blocks most of them. At LZ's heart sits a titanium tank containing 7 tons of ultra-pure liquid xenon, chilled to minus 100 degrees Celsius. Xenon is ideal for dark matter detection because it's dense. It's a noble gas that's chemically inert and reduces contamination, and it produces light and electrical signals when particles interact with it. The xenon is surrounded by layers of shielding. More xenon to catch particles trying to enter from the sides, then water to absorb neutrons and gamma rays, then the cavern rock itself. Every material is carefully selected for ultra-low radioactivity. Even the titanium vessel is specially manufactured to minimize contamination from natural radioactive isotopes. The detector works on a simple principle. Wait for a WIMP to hit a xenon nucleus. When a particle strikes a xenon atom, it causes the atom to recoil, creating a flash of ultraviolet light and liberating electrons. An electric field pulls these electrons toward the top of the detector, where they're extracted from the liquid into a layer of gaseous xenon. There, they create a second flash of light that's proportional to the energy deposited. By measuring the relative strength and timing of these two signals, physicists can determine how much energy was deposited, where in the detector the interaction occurred, and what type of particle caused it. WIMPs produce different signal ratios than other particles. The detector is so sensitive that it can detect a xenon nucleus recoiling with energy equivalent to a mosquito pushing against your hand. And it can distinguish this from background noise with extraordinary precision. In December 2025, just breaking news, the LZ collaboration announced remarkable results from 417 days of data collection. They didn't detect dark matter, but what they achieved was almost as significant. They detected neutrinos from the Sun's core through coherent elastic neutrino nucleus scattering, CEVNS. Braster, and they set the most stringent limits yet on dark matter interaction rates. Let me explain why detecting solar neutrinos through CEVNS matters. Neutrinos are ghostly particles produced in nuclear reactions, including the fusion reactions powering the sun. They barely interact with matter, similar to dark matter in this respect, though for different physics reasons. Billions of neutrinos from the sun pass through your thumbnail every second. Almost all pass right through Earth without interacting. LZ's detection of solar neutrinos through CEVNS proves the detector is sensitive enough to catch incredibly rare interactions. It validates the calibration, confirms the sensitivity is as designed, and demonstrates that the background rejection is working. As Scott Kravitz from the University of Texas at Austin and the analysis coordinator for LZ explained, this result is clear confirmation that LZ could observe even low-mass dark matter. It means the detector and our experiment are as sensitive as expected and capable of finding dark matter if it's within the range where we're searching. The dark matter limits are equally important. LZ has ruled out certain types of WIMPs with unprecedented sensitivity. If dark matter particles interact with xenon nuclei at rates above certain thresholds, LZ would have seen them. It didn't. This constrains theoretical models and tells particle physicists where not to look. But LZ faces an interesting challenge going forward. The detector has now become so sensitive that it's entering what's called the neutrino fog. Neutrinos, while rare, aren't as rare as WIMPs might be. As detectors become more sensitive, they start detecting neutrinos from various sources: the sun, the atmosphere, even supernovae in distant galaxies. These neutrino interactions can potentially mimic dark matter signals. This neutrino fog represents a fundamental background that can't be shielded against. Neutrinos pass through any amount of rock, water, or metal without stopping. If you want to detect faint dark matter signals, you must develop techniques to distinguish them from this neutrino background. This is where AI is beginning to play a crucial role. The same pattern recognition capabilities that help AI map dark matter through gravitational lensing are now being applied to direct detection experiments. When a particle interacts in the LZ detector, it doesn't just produce two flashes of light, and it produces complex waveforms, detailed time series of photon arrivals at hundreds of individual photomultiplier tubes surrounding the detector. The exact shape of these waveforms, their timing, and their spatial distribution all contain information about what kind of particle caused the interaction. Traditionally, physicists analyze these waveforms using carefully designed algorithms based on physics understanding. They look for specific features they know distinguish different particle types: signal rise times, pulse widths, ratios between top and bottom detector sections, correlations across multiple sensors. These traditional methods work well, but they may not extract all available information. The waveforms are high-dimensional and complex. There might be subtle patterns or correlations that no human has thought to look for. And machine learning offers a complementary approach. Train a neural network on calibration data where you know what particle caused each interaction, perhaps using a neutron source for neutron calibrations, or using tagged muon events for muon calibrations. Let the network learn to distinguish different particle types based on the full waveform complexity. Several direct detection experiments are now implementing such machine learning-enhanced analysis. Pattern recognition algorithms identify signal-like events with higher efficiency than traditional cuts. Anomaly detection systems flag unusual waveforms that don't match any known particle type, potentially including new physics. Regression networks estimate interaction energies and positions with improved precision. Classifier networks better separate nuclear recoils, potential WIMP signals, from electron recoils, which are backgrounds. These AI systems aren't replacing human physicists. Rather, they're becoming part of the analysis toolkit. complementing traditional methods and sometimes revealing aspects of the data that weren't previously appreciated. LZ isn't alone in the quest to directly detect dark matter. Around the world, several major experiments employ similar liquid xenon technology, creating a friendly competition and collaboration. The Xenon Collaboration operates detectors at Gran Sasso National Laboratory in Italy, deep underground in a tunnel through the Apennine Mountains. Their latest detector, Xenon NT, contains 8.3 tons of liquid xenon, even larger than LZ. In China, the Pandex Collaboration runs detectors in the Jinping Underground Laboratory, located 7,900 feet beneath Marble Mountains, the deepest underground laboratory in the world. The additional depth provides extra shielding from cosmic rays. Each experiment has slightly different design choices, different purification systems, different calibration strategies. This diversity is valuable. If one experiment sees a signal, independent confirmation by another experiment with different systematic uncertainties would be crucial for establishing a discovery. These experiments share data, techniques, and machine learning tools. AI developed for one detector often proves useful for another. The neural networks learn detector-specific features, but the general architectures and training approaches transfer. And while the evidence for dark matter is overwhelming, science progresses by testing alternative explanations. The most prominent alternative is MOND, modified Newtonian dynamics. MOND, proposed by physicist Mordechai Milgram in 1983, suggests that rather than invisible matter, gravity itself behaves differently at very low accelerations, the accelerations experienced by stars in the outer regions of galaxies. In MOND, Newton's law of gravity is modified when accelerations fall below a critical threshold, about 1/10,000,000th of Earth's surface gravity. Below this threshold, gravity becomes stronger than Newton predicts, explaining why outer stars and galaxies orbit faster than expected without requiring dark matter. MOND successfully reproduces galaxy rotation curves, the observations that initially led to dark matter's discovery. This is its strength, but it struggles to explain other observations: the cosmic microwave background radiation patterns, the distribution of galaxy clusters, gravitational lensing by galaxy clusters where the lensing mass is clearly separated from visible matter, the collision of galaxy clusters like the bullet cluster, where dark matter and normal matter have visibly separated. Recent AI-powered analysis has subjected MOND to new tests. Researchers used machine learning to analyze precisely measured stellar systems, globular clusters and dwarf galaxies, where both the visible matter distribution and the kinematics, how stars move, are well characterized. They trained neural networks on simulations of these systems under both standard gravity plus dark matter and under MOND dynamics. The networks learned characteristic signatures that distinguish the two scenarios. When applied to real observations, the results strongly favored standard physics with dark matter over MOND. This doesn't definitively rule out modified gravity theories. There are more sophisticated variants of MOND, and perhaps some yet unconceived theory could explain all observations without dark matter. But AI is helping test these alternatives with unprecedented rigor, using the full complexity of the data rather than simple summary statistics. To truly appreciate dark matter's importance, you must understand what the universe would look like without it. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were tiny variations in density. Quantum fluctuations stretched to cosmic size by cosmic inflation. But these variations were small, perhaps 1 part in 100,000. Over time, gravity amplified these tiny variations. Regions slightly denser than average pulled in more matter, becoming denser still. Regions slightly less dense than average lost matter, becoming voids. This is gravitational instability, the process by which structure grows. But here's the crucial point. This process works far too slowly with normal matter alone. Normal matter, protons, neutrons, electrons, interacts with light through electromagnetic forces. In the early universe, when everything was hot and dense, matter and light were tightly coupled. Photons couldn't travel far before bouncing off electrons. And this photon pressure prevented normal matter from collapsing into dense clumps. Only after the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, did light decouple from matter. Finally, normal matter could begin clumping under gravity's pull. But 380,000 years is a long delay. If structure formation relied solely on normal matter clumping after this point, the universe today would look nothing like what we observe. Galaxies wouldn't have formed until recently, perhaps just a few billion years ago. The cosmic web would be much less pronounced. Large galaxy clusters might not exist at all. Dark matter changes everything. Dark matter doesn't interact with light. It's not impeded by photon pressure. So dark matter could begin clumping immediately after the Big Bang, and long before normal matter decoupled from radiation. By the time atoms formed and normal matter was free to move, dark matter had already created gravitational wells, concentrations dense enough to rapidly pull in normal matter. Normal matter fell into these dark matter halos, accumulating in the centers where it became dense enough to form stars. The first stars likely formed in small dark matter halos just a few 100 million years after the Big Bang, far earlier than would be possible without dark matter. Over billions of years, these small halos merged, building ever larger structures. Small halos became galaxy-sized halos. Galaxy-sized halos merged into group-sized halos. Groups merged into clusters. And the entire cosmic web, the filamentary structure of galaxy distribution throughout the universe, emerged from dark matter's early head start. Without dark matter, none of this structure would exist. No galaxies, no stars, no planets, no life. Understanding how cosmic structure forms requires thinking across enormous ranges of scale and time. Start with the cosmic microwave background. The afterglow of the Big Bang, emitted 380,000 years after the universe began. This radiation has tiny temperature fluctuations, about 0.001% variations from place to place. These fluctuations map the density variations in both dark matter and normal matter at that early time. Galaxies preserve evidence of their formation histories in their current properties, like fossils recording ancient events. For example, stellar populations. Old stars in a galaxy formed long ago from less enriched gas. Young stars formed recently from gas enriched by previous generations of stars that lived, died, and dispersed heavy elements. By analyzing the mix of stellar ages and chemical compositions, astronomers can reconstruct when major star formation episodes occurred, which correlates with when the galaxy's dark matter halo experienced major mergers. Morphology tells a story too. Spiral galaxies tend to form in halos that have experienced quiet merger histories, accumulating gas gradually and forming rotating disks. Elliptical galaxies often result from major mergers between spirals, violent events that disrupt orderly rotation and create randomly oriented stellar orbits. The morphological mix of galaxies tests theoretical predictions for merger rates. Used dark matter halo profiles also reveal formation history. The distribution of dark matter within a halo depends on the halo's assembly history. Halos that formed early and experience many mergers tend to have more concentrated profiles. Halos that formed late from smooth accretion tend to have shallower profiles. Measuring these profiles through lensing or stellar kinematics reveals formation history, AI systems are now being trained to infer galaxy formation histories from these fossil records. A neural network might analyze a galaxy's image, spectrum, and local environment, then predict when the galaxy's dark matter halo first collapsed, how many major mergers it has experienced, its star formation history over cosmic time, and the current mass and profile of its dark matter halo. These inferred histories can be compared to predictions from cosmological simulations, testing our understanding of how dark matter drives structure formation. Despite dark matter's success in explaining cosmic structure on large scales, tensions exist between theory and observation on smaller scales. One example is the missing satellites problem. Simulations predict that large galaxies like the Milky Way should be surrounded by thousands of small dark matter halos, remnants of the hierarchical assembly process. Most of these halos should not contain visible galaxies, they'd be dark halos. But hundreds should contain small dwarf galaxies orbiting as satellites. However, observations find far fewer satellite galaxies than predicted. The Milky Way has a few dozen known satellites, not hundreds. This discrepancy is puzzling. Possible explanations include suppressed star formation. Perhaps most small halos never formed stars, making them invisible. Various astrophysical processes could suppress star formation in small halos. Photoionization from the cosmic UV background preventing gas from cooling, supernova feedback expelling gas before many stars form, or tidal stripping removing gas as halos orbit through larger galaxies. Observational incompleteness is another possibility. Perhaps the satellites exist, but are too faint to detect with current surveys. AI-powered searches of deep imaging data are discovering ever fainter dwarf galaxies, gradually filling in the count. Each new dwarf discovered brings observations closer to predictions. Or perhaps modified dark matter physics is needed. Perhaps dark matter isn't cold, moving slowly, as usually assumed, but warm, moving faster. Warm dark matter would prevent very small halos from forming, naturally explaining why we don't see numerous tiny satellites. Or perhaps dark matter self-interacts, changing the structure of small halos. Resolving this requires both better observations, finding all the faint satellites that exist, and better simulations, accurately modeling star formation and feedback in small halos. AI helps on both fronts, discovering satellites in imaging data and analyzing simulations to understand which halos should host visible galaxies. The internal dynamics of galaxies provide another testing ground for dark matter models. Inside a galaxy, stars, gas, and dark matter all contribute to the gravitational potential. Stars orbit within this potential, their velocities determined by the total mass distribution. By measuring stellar velocities throughout a galaxy, using spectroscopy to measure Doppler shifts, astronomers can infer the mass distribution, including dark matter. This is how Vera Rubin originally discovered dark matter. Galaxy rotation curves remain flat at large radii, implying dark matter halos extending beyond the visible disk. Modern observations go far deeper. Using integral field spectroscopy, astronomers measure not just how fast stars orbit, but in what directions and with what velocity dispersions. This reveals the full orbital structure. Do stars follow circular orbits in a disk, or elongated orbits in a spheroid? How much random motion do they have versus ordered rotation? AI systems can analyze these complex kinematic data to infer dark matter distributions with unprecedented detail. Neural networks learn the relationship between observed kinematics and underlying mass profiles through simulations, then apply this knowledge to real galaxies. Such analyses reveal how dark matter halos are shaped, spherical, oblate, or triaxial, whether dark matter and baryonic matter are aligned or misaligned in their orientations. how dark matter density profiles vary from galaxy to galaxy. Whether profiles match predictions from collisionless cold, dark matter simulations. Each measurement tests theoretical predictions and constrains dark matter's properties. One of the most complex aspects of galaxy formation is feedback. How star formation and black hole growth affect their environments. When massive stars form, they live short, violent lives. They emit intense ultraviolet radiation that ionizes surrounding gas. When they drive powerful stellar winds that push gas away. And when they die as supernovae, they inject enormous energy into their surroundings. A single supernova releases as much energy as the sun emits in its entire 10 billion year lifetime, concentrated in a few weeks. This feedback can blow gas out of galaxies entirely, especially small galaxies with weak gravitational potential wells. It can heat gas to such high temperatures that it cannot cool and form new stars for millions of years. It can create bubbles and cavities in the gas distribution. Supermassive black holes in galaxy centers provide even more extreme feedback. When actively accreting matter, they produce active galactic nuclei, luminous regions outshining entire galaxies. The energy from AGN can heat gas throughout a galaxy, or drive powerful outflows that expel gas at thousands of kilometers per second. This feedback affects dark matter indirectly by redistributing baryonic matter. Moving baryons around changes the gravitational potential, which affects dark matter orbits. Vigorous feedback can actually make dark matter halos less centrally concentrated. The dark matter responds to the changing potential by moving outward. Simulating these feedback processes requires resolving physics on enormous dynamic range. From the event horizons of black holes to individual supernova explosions to galaxy-wide gas flows to cosmological structure formation. No single simulation can resolve all these scales simultaneously. This is where AI offers new approaches. Rather than simulating every detail, researchers train neural networks on high-resolution simulations of small volumes, then use these networks as sub-grid models in large-volume cosmological simulations. The network learns to predict the net effect of feedback on scales the large simulation can't resolve. Based on the local environment, the simulation can resolve. This lets simulations include realistic feedback while still tracking dark matter structure formation across cosmological volumes, getting the best of both detailed physics and large-scale statistics. The next frontier in direct dark matter detection is already being planned. XLZD, the ultimate successor to experiments like LZED, Xenon, and Panda-X. XLZD, which stands for Xenon Light Detector, will use liquid xenon targets 10 times larger than current experiments. Instead of 7 tons of active xenon like LZ, the XLZD will deploy 70 tons. This 10-fold increase in mass means a 10-fold increase in the number of potential dark matter interactions, dramatically improving sensitivity. But size isn't everything. XLZD will also incorporate advances in purification, shielding, and readout technology. Improved purification is crucial. Every radioactive atom in the detector is a potential background. Even ultra-pure xenon contains trace amounts of radioactive isotopes. XLZD will push purification to new extremes, reducing these contaminants to levels below 1 part per trillion. Better shielding will filter out ambient radiation. Beyond the detector vessel, multiple layers of shielding will absorb neutrons and gamma rays. Water, polyethylene, and lead provide protection. The rock overburden absorbs cosmic rays. Every material is selected for minimum radioactivity. Advanced readout technology will be more sensitive. The photodetectors that capture scintillation light will have lower background. Silicon photomultipliers may replace traditional photomultiplier tubes, offering better quantum efficiency and lower radioactive contamination. But here's the interesting challenge. Even with all these improvements, XLZE will be operating well into the neutrino fog. Solar neutrinos, atmospheric neutrinos, and even neutrinos from distant supernovae will create interactions that must be distinguished from potential dark matter signals. This is where AI will be essential. Machine learning algorithms, trained on the full complexity of interaction waveforms, will maximize the separation between neutrino-induced events and potential WIMP signals. The pattern recognition techniques will identify subtle signatures in the data that traditional analysis might miss. The goal is to either detect dark matter definitively or rule out the most popular WIMP models completely. Either outcome would be revolutionary. Discovery obviously so. But even null results would redirect the field toward alternative dark matter candidates or detection strategies. An unexpected tool for studying dark matter has emerged from gravitational wave astronomy. Gravitational waves, ripples in spacetime caused by accelerating masses, were directly detected for the first time in 2015. Since then, observatories have detected dozens of events, from merging black holes and neutron stars. These gravitational wave sources are valuable as standard sirens, cosmic distance indicators similar to supernovae. By measuring both the gravitational wave signal, which gives distance, and the electromagnetic signal identifying the host galaxy, which gives redshift, astronomers can measure how the universe's expansion rate changes over cosmic history. This expansion history is sensitive to dark matter and dark energy. More dark matter means stronger gravitational deceleration. More dark energy means stronger acceleration. The precise balance determines how cosmic expansion evolves. AI plays a crucial role in gravitational wave astronomy. Machine learning algorithms search for faint signals buried in detector noise, signals too weak for traditional matched filtering. Neural networks classify events, distinguishing real astrophysical sources from instrumental glitches. And pattern recognition helps identify electromagnetic counterparts in wide-field images. Furthermore, dark matter itself might produce gravitational waves. If dark matter consists of primordial black holes formed in the early universe rather than from stellar collapse, then mergers of these primordial black holes would create gravitational waves. The mass distribution and merger rates would differ from stellar mass black hole mergers, potentially providing a distinctive signature. AI analysis of gravitational wave catalogs is searching for such signatures, testing whether any fraction of detected mergers might involve primordial black holes rather than stellar remnants. Scheduled for launch in 2027, the Nancy Grace Roman Space Telescope will revolutionize dark matter research yet again. A Roman, named after NASA's first chief of astronomy, who championed space telescopes and fought for opportunities for women in science, carries a 2.4-meter mirror, the same size as Hubble's. But its field of view is 100 times larger. In a single image, Roman can capture an area of sky equivalent to 100 Hubble images. This combination of resolution and field of view makes Roman uniquely suited for mapping dark matter through weak gravitational lensing. Over its primary mission, Roman will survey 2,000 square degrees, about 5% of the sky, imaging hundreds of millions of galaxies with extraordinary clarity. The data volume will exceed even Euclid's. Billions of galaxy images, each requiring shape measurement, photometric redshift estimation, and lensing analysis. Processing this will require the most sophisticated AI systems ever applied to astronomy. Roman's survey will map dark matter in 3D. By measuring photometric redshifts, approximate distances based on galaxy colors, Roman will place lensing measurements at different distances, building a three-dimensional map of dark matter structure from the early universe to today. It will measure the growth of structure. Comparing dark matter clustering at different cosmic epochs reveals how structure has grown over time, which is sensitive to dark energy's properties and tests general relativity on cosmic scales. Roman will discover rare lensing events. The telescope will find thousands of strong lensing systems, rare cases where foreground mass creates multiple images or dramatic arcs of background sources. Each strong lens precisely measures the mass distribution in the foreground, including dark matter, and it will survey thousands of supernovae. Type 1. Sappersalpt, A supernovae are standard candles for measuring cosmic distances. Roman will discover and measure thousands of supernovae, refining measurements of dark energy and testing for evolution in supernova properties over cosmic time. AI will be integral to every aspect of Roman's data analysis, from real-time transient detection to cosmological parameter inference. An entirely new class of dark matter experiments is emerging based on quantum sensing, using quantum mechanical systems as ultra-sensitive detectors. Traditional direct detection, like LZ, searches for dark matter scattering off atomic nuclei. This works for WIMPs with masses around 10 to 1,000 times the proton mass. But what if dark matter is much lighter? Or what if it doesn't scatter at all, but instead is absorbed like a photon? Quantum sensors can search for these alternatives. Atomic clocks, extraordinarily precise atomic clocks, can detect dark matter passing through if it causes subtle shifts in fundamental constants or creates oscillations in atomic energy levels. Networks of synchronized clocks can detect waves of dark matter sweeping through Earth. Superconducting qubits, the same superconducting circuits used for quantum computing, are sensitive to energy depositions from particle interactions. They could detect dark matter particles lighter than those accessible to traditional detectors. Optomechanical resonators, tiny mechanical oscillators monitored with laser interferometry, can detect forces from dark matter interactions. These devices can search for dark matter much lighter than atoms. Magnetic resonance techniques, nuclear magnetic resonance and electron spin resonance, can detect dark matter that couples to nuclear or electron spins, probing entirely different interaction types than traditional experiments. Each of these quantum sensing approaches generates complex data requiring sophisticated analysis to distinguish signals from noise. AI is increasingly employed for real-time signal processing and anomaly detection, background modeling and subtraction, correlation analysis across multiple sensors, and statistical inference for weak signals near detection thresholds. As quantum sensors improve and datasets grow, machine learning will become essential for extracting discovery-level sensitivity from these novel detection approaches. Axions represent an alternative dark matter candidate with very different properties from WIMPs. An axion is an extremely light particle, billions of times lighter than an electron, proposed to solve the strong CP problem in particle physics. If dark matter consists of axions, they would behave as a quantum field pervading space rather than as individual particles zipping around. The Milky Way's dark matter halo would be an oscillating axion field with frequency determined by the axion's mass. This field can convert to photons in the presence of strong magnetic fields. Axion detection experiments use this principle. Resonant cavities use a microwave cavity in a strong magnetic field to convert axion dark matter into photons. By tuning the cavity's resonance frequency, the experiment searches different axion masses. Our haloscopes are similar to cavities, but with different geometries and technologies designed to search particular mass ranges. Helioscopes point detectors at the Sun, where axions might be produced in the core and convert back to photons in a magnetic field on Earth. The challenge is that you don't know the axion mass in advance, so you must search across a huge range of possible frequencies. Similar to searching a radio dial for a faint signal without knowing what station it's on. Traditional searches scan frequency slowly, dwelling at each frequency long enough to integrate down noise. This is time-consuming. AI offers new strategies. The ADMX experiment, the Axion Dark Matter experiment, is the world's most sensitive axion haloscope operating at the University of Washington. ADMX uses machine learning for rapid scanning with signal detection algorithms that can identify candidate signals in real time, even when they're only marginally above noise. Multi-frequency correlation looks for correlations across multiple frequencies that might arise from axion physics or experimental systematics. Adaptive search strategies use reinforcement learning to optimize search strategies, spending more time on promising frequency ranges and less on regions that appear empty. These AI-enhanced searches are accelerating the hunt for axions, covering more parameter space faster than traditional approaches. Looking ahead, the next decade of dark matter research promises extraordinary discoveries. Multiple lines of investigation are converging. Observational cosmology, Euclid, Roman, the Vera Rubin Observatory, and cosmic microwave background experiments will map dark matter structure with exquisite precision, constraining its properties and testing alternative theories. Direct detection, XLZD, and other next-generation experiments will either discover WIMPs or rule them out decisively, potentially redirecting the field. Accelerator searches. The Large Hadron Collider's high luminosity upgrade and proposed future colliders might produce dark matter particles in collisions, allowing laboratory study. Quantum sensors. Novel detection technologies will probe lighter dark matter candidates and different interaction types. Multi-messenger astronomy. Combining gravitational waves, neutrinos, electromagnetic observations, and cosmic rays will test dark matter models in new ways. AI will be integral to all of these efforts, most analyzing data sets too large and complex for traditional methods, discovering unexpected patterns, and enabling discoveries that would otherwise remain hidden. What would it mean to solve the dark matter mystery? A complete solution would identify what dark matter is made of, detect dark matter particles directly, measure their properties, mass, interaction cross-sections, possibly internal structure, and confirm these particles exist in the abundance needed to explain cosmic observations. It would help us understand how it behaves, map dark matter's distribution from the smallest dwarf galaxies to the largest superclusters, test whether it behaves as predicted by collisionless cold dark matter, and measure any self-interactions or couplings to normal matter. We would learn where it came from, determine how dark matter was produced in the early universe, whether in thermal equilibrium during the Big Bang, through some phase transition, or by other mechanisms. And we could integrate it into fundamental physics. Connect dark matter to other physics. Does it relate to the matter-antimatter asymmetry? To the hierarchy problem in particle physics? To quantum gravity? Success might not come from a single dramatic discovery, but from accumulating evidence across multiple experiments and observations, gradually building a complete picture. Or perhaps there will be a eureka moment, a clear detection in a direct detection experiment, simultaneously confirmed by different technology, with particles matching predictions from accelerator searches and consistent with all cosmological observations. Either way, AI will be central to recognizing the pattern, connecting dots across different experiments and datasets, and extracting the maximum information from every observation. The discovery of dark matter represents another step in a long series of cosmic demotions for humanity. For millennia, humans believed Earth was the center of the universe. with celestial bodies revolving around our world. Copernicus demolished this geocentrism, showing Earth orbits the Sun like other planets. Later, astronomers showed the Sun is not central either, just one star among hundreds of billions in the Milky Way, located not in the galaxy's center, but in a nondescript spiral arm. Then Edwin Hubble revealed that the Milky Way itself is just one galaxy among billions, scattered throughout an expanding universe with no special center, where dark matter adds another layer to this cosmic humility. Not only are we not central to the universe's structure, we're not even made of the primary material of reality. Normal matter, the protons, neutrons, and electrons composing stars, planets, and people, is a minority constituent. The universe is primarily built from dark matter, with normal matter as almost an afterthought. Everything humans have ever observed directly, every atom we've touched, every photon we've seen, represents just a small fraction of cosmic reality. We're not just displaced from the center, we're made of the universe's rare, exotic ingredient. Yet, this is not a diminishment, but an expansion. We've learned that reality is far vaster, stranger, and more interesting than our ancestors imagined. The universe isn't built to human scale, nor from human familiar materials. And somehow, we, made of this rare 5%, have developed the capacity to study and understand the invisible 95%. Understanding dark matter changes how we understand cosmic history. The story of the universe is not primarily the story of stars, galaxies, and light. It's the story of dark matter, with luminous matter playing a supporting role. Dark matter clumped first, creating gravitational wells. Normal matter fell into these wells, forming the first stars and galaxies. Dark matter mergers drove galaxy mergers. Dark matter's gravitational scaffolding determined where and when structure formed. Even the existence of life may depend on dark matter. Without dark matter's early head start in structure formation, our galaxies might have formed too late for multiple generations of stars to create the heavy elements necessary for planets and life. Without dark matter halos holding galaxies together, stellar orbits might be unstable, preventing long-term stability needed for biological evolution. In a real sense, we owe our existence to dark matter, despite never directly interacting with it. This realization invites philosophical reflection. The most important constituents of reality are often invisible, intangible, yet profoundly influential. Dark matter shapes cosmic structure without shining. Dark energy drives cosmic expansion without being localized anywhere. These hidden forces are primary. The visible universe is derivative. Perhaps there's a lesson here about humility and perspective, about recognizing that what we can directly observe or experience may not be what primarily matters. The hunt for dark matter also illuminates something about intelligence itself, both human and artificial. Human intelligence excels at asking questions, formulating theories, designing experiments, recognizing anomalies, synthesizing knowledge across domains, and finding meaning in discoveries. Artificial intelligence excels at processing vast datasets, recognizing subtle patterns in high-dimensional data, optimizing complex systems, and discovering correlations that no human would think to look for. Dark matter research showcases how these intelligences complement each other. Humans conceive dark matter as a hypothesis, design detection strategies, built detectors and telescopes, and develop the physical theories that frame our understanding. AI processes the resulting data, finding patterns that reveal dark matter's distribution, extracting signals from noise, and pushing sensitivity beyond what traditional analysis allows. Neither could solve this mystery alone. Human intuition without AI would drown in data, missing subtle signals. AI without human guidance would lack the theoretical framework to know what patterns are physically meaningful. The future of science, especially big science dealing with enormous data sets and complex phenomena, will be characterized by this partnership. Human scientists will increasingly work with AI collaborators, each contributing their unique strengths. This raises interesting questions about understanding and discovery. When an AI finds a pattern that leads to a breakthrough, who made the discovery? The scientists who built the AI, trained it, and interpreted its outputs. The AI itself? The partnership? Perhaps the question is misframed. Discovery is a process, not a moment. It involves conceiving questions, developing methods, gathering data, analyzing results, and interpreting meaning. Different intelligences contribute to different stages. The whole process is discovery, and both human and machine intelligence are essential to it. Dark matter research also invites reflection on why we pursue knowledge that has no immediate practical application. Searching for dark matter won't cure diseases, won't solve climate change, won't feed the hungry. The particles detected by LZ, if ever detected, will have zero direct impact on daily human life. The maps of dark matter from Euclid won't change how anyone lives. So why spend billions on these endeavors? The answer touches on what makes us human. We are meaning-seeking creatures. We want to understand our place in the cosmos, to know what reality is made of, to comprehend the forces that shape existence. This desire for understanding is as fundamental as hunger or reproduction. It's expressed in every culture through mythology, religion, philosophy, and science. The methods change, but the drive remains constant. Moreover, the pursuit of fundamental knowledge has historically led to unexpected practical benefits. Quantum mechanics, developed to understand atomic structure, now underpins electronics, lasers, and quantum computing. Einstein's relativity, pursued for purely theoretical reasons, is necessary for GPS satellite systems. Particle physics research led to the World Wide Web. We can't predict which discoveries will prove useful or how. But history suggests that expanding our understanding of nature eventually expands our capability to shape it. Perhaps more importantly, the pursuit itself is valuable. Building detectors like LZ requires pushing technology to its limits. Developing ultra-pure materials, exquisitely sensitive sensors, and sophisticated data analysis. These technological advances find applications beyond their original purpose. Similarly, AI developed for astronomical data analysis often transfers to other domains: medical imaging, climate modeling, financial analysis, genomics. Techniques pioneered for finding dark matter in telescope images can detect tumors in medical scans or predict crop yields from satellite imagery. The pursuit of fundamental knowledge is not separate from practical concerns. It's intertwined with technological development, with training the next generation of scientists and engineers, with inspiring wonder and curiosity, and with building capabilities that eventually serve countless purposes. There's a beautiful symmetry between looking outward to the cosmos and inward to the quantum realm. Dark matter research operates at the largest scales: galaxies, clusters, the cosmic web. Yet it also requires probing the smallest scales: individual particle interactions, quantum fluctuations, the properties of elementary particles. Euclid looks outward across billions of light years, in a mapping structure on cosmic scales. LZ looks inward, monitoring individual xenon atoms for the faintest interactions. Both approaches seek the same truth. What is dark matter made of? How does it behave? What role does it play in cosmic evolution? This convergence of the very large and very small is characteristic of modern physics. Cosmology and particle physics, once separate fields, are now intimately connected. Understanding the early universe requires particle physics. Understanding dark matter requires both cosmological observations and particle detection. AI bridges these scales, analyzing cosmic surveys and direct detection experiments with the same fundamental techniques. Neural networks trained to recognize patterns, whether those patterns span megaparsecs or microns. This unity of understanding, connecting the largest and smallest phenomena through common physical principles, is one of science's great achievements. And it's an achievement that artificial intelligence is now accelerating. It's fitting that the observatory set to revolutionize dark matter research bears Vera Rubin's name. Rubin faced obstacles that had nothing to do with scientific merit. Barriers erected simply because she was a woman in a field dominated by men. She was excluded from observatories, told her work wasn't important, denied credit for discoveries. Yet she persisted. Her observations of galaxy rotation curves provided some of the strongest evidence for dark matter. Her meticulous work forced the scientific community to take dark matter seriously. And she never received a Nobel Prize, despite transforming our understanding of the universe. Naming a revolutionary observatory after her is partial redress for that oversight. But it's also recognition that progress requires both scientific excellence and social progress. How many other Vera Rubins were prevented from contributing because of barriers based on gender, race, class, or nationality? How much faster would science advance if everyone with ability had equal opportunity? The partnership between human and artificial intelligence in dark matter research offers a hopeful vision. A future where discoveries come from global collaboration, where the best ideas win regardless of their source, where opportunity is limited only by curiosity and talent. AI doesn't care about a scientist's gender, race, or background. It responds only to the quality of training data, the cleverness of architecture, and the insight behind its application. In principle, this could democratize discovery, making major contributions accessible to anyone with the right ideas and the ability to implement them. Of course, AI also risks perpetuating and amplifying existing inequalities if developed and deployed without care. Training data can embed biases. Access to computational resources is unevenly distributed. The benefits of AI capability might accumulate to already advantaged groups. Ensuring that AI serves all of humanity, advancing science for everyone's benefit, requires conscious effort. It requires diverse teams building AI systems, equitable access to data and compute, and commitment to open science. The dark matter research community has generally embraced these values. With data publicly released, methods openly shared, and international collaboration the norm. This ethos should extend to AI development. Finally, it's worth reflecting on the wonder inherent in dark matter's mystery. We live in an age of tremendous knowledge. Humans have mapped genomes, split atoms, visited other planets, and decoded the cosmic microwave background. We understand nature across dozens of orders of magnitude in size and energy. Yet the universe still holds profound mysteries. Dark matter, dark energy, the nature of quantum measurement, the origin of cosmic structure, consciousness, the arrow of time. These mysteries aren't failures of science. They're invitations to discovery, reminders that reality exceeds our current understanding, promises of revolutions yet to come. Dark matter exemplifies this perfectly. We know it exists with extraordinary confidence. We've measured its amount and mapped its distribution. We understand its crucial role in cosmic history. But we don't know what it is. After decades of searching, this fundamental question remains unanswered. This should inspire humility and excitement in equal measure. Humility because nature is teaching us again that our intuitions and theories are incomplete. Excitement because we're on the verge of discoveries that will transform our understanding. And we're not hunting alone. We have artificial allies, intelligences capable of seeing patterns we cannot see, processing data at scales we cannot reach, and revealing secrets hidden in plain sight since the dawn of time. Together, human curiosity and artificial intelligence, we're writing the next chapter in our cosmic story, a one where the darkness itself becomes a source of light. The invisible 85% of reality is finally coming into focus. Pixel by pixel, algorithm by algorithm, revealing the dark foundations upon which our bright universe stands. What we discover there may surprise us, may challenge us, and may ultimately help us understand not just what the universe is made of, but why anything exists at all. As you watch this, dark matter flows through you. Trillions of particles, perhaps WIMPs, perhaps axions, perhaps something we haven't yet imagined, passing through your body without leaving a trace. They carry no charge, emit no light, feel no force except gravity's gentle tug. Yet they are real as the atoms in your hand, as real as the light from the sun. They outnumber normal atoms 6 to 1. They shaped every galaxy. They determined where stars would form and set the initial conditions for planetary systems and life itself. Scientists and their AI collaborators are closing in on dark matter's secrets. Each observation from Euclid brings new precision to cosmic maps. Each day of data from LZ pushes deeper into unexplored parameter space. Each neural network trained on simulated universes learns to extract more information from less data. The breakthrough could come tomorrow, when a detector deep underground registers an unambiguous dark matter interaction, confirmed by independent experiments, matching theoretical predictions. Or it could come years from now, gradually emerging from accumulated evidence. Maps showing structure inconsistent with any alternative theory, multiple detection methods converging on consistent particle properties, accelerator experiments producing particles matching astrophysical observations. However it comes, the discovery will reshape physics. It will answer questions about the universe's composition, structure formation, and ultimate fate. It might point toward deeper physics, unification of forces, extra dimensions, or connections between dark matter and other mysteries. And artificial intelligence will be central to this discovery, not as a tool, but as a partner. AI systems that can see invisible patterns in cosmic structure, that can distinguish faint signals from overwhelming noise, that can synthesize evidence across different experiments and observations. These digital detectives are revealing the universe to us in ways no previous generation could have imagined. They're extending human capability, so compensating for our limitations in processing speed and scale, while still depending on human guidance, human creativity, and human wisdom to frame questions and interpret answers. This is science in the 21st century, a collaboration between biological and artificial intelligence, each contributing unique strengths, together pushing the boundary of human knowledge further than either could alone. The hunt for dark matter continues, and perhaps, in pursuing this invisible majority of cosmic matter, we're learning something profound, not just about the universe, but about ourselves. We're learning that the most important things are often invisible, hidden from direct observation, but revealed through their effects. We're learning that reality exceeds our intuition, that nature is stranger and more wonderful than we imagine. Like we're learning that mysteries persist even as knowledge grows, that answering questions generates new questions, that the frontier of ignorance expands as fast as the frontier of knowledge. Most importantly, we're learning that intelligence takes many forms, carbon-based and silicon-based, evolved and designed, intuitive and analytical. And that together, these different forms of intelligence can achieve what none could alone. Vera Rubin once said, "There's no problem in science that can be solved by a man that cannot be solved by a woman." Today we might add, there's no cosmic mystery so complex that it cannot be illuminated by the partnership between human curiosity and artificial intelligence.